Hello. Good afternoon everyone. So we will discuss today's tutorial 7 for the physics of material classes. So we will discuss first last 7th week what's are taught in the class. We briefly explain here, then we will go to the problem solving section. So in last class first we started about the Roots model and from Roots-Sommerfeld model. So here what we have discussed is like electrons in metal. So we are saying that there will be electrons are free. So here we do not see the ionic cores of the solid, we will see the free electrons. So in Roots model we have discussed that electrons are like gases. Look, we have followed the classical gases, that's why we followed the Maxwell-Boltzmann statistics. But then we have told that the classical particles are identical but they are distinguishable. Okay. So in reality what will happen, the electrons which are the quantum particles and they are indistinguishable and identical. So they follow the Pauli's exclusion principle. So they follow the statistics which is called Fermi-Dirac statistics. So then what we have done is like we have included the Fermi-Dirac statistics. Like in electron case we have to discuss the Fermi-Dirac statistics. So then we have found specific heat of that particular material. So Maxwell-Boltzmann's equation we have used for that, when which is like CV value which is 100 times more than the actual value. So these whole things we have discussed in last week. So in both model, like Roots model and Roots-Sommerfeld model, both case we consider electrons as free. So but in reality if we consider solid, it will has ionic cores. So what will happen, these ionic cores will give the electrons which passes around the solids. Okay. So this free electron model we cannot consider as in the ionic cores. So what are the models which we learn, that is Roots model and Sommerfeld model, and these two are the free electron models. So now we will say that the electron will see the ionic core. So actually in solids we can consider the metal we can consider the ionic cores as well as the free electrons. So as if now we have discussed it only case of free electron, we didn't consider the ionic cores. That's two models we have which is discussed, Roots model and Roots-Sommerfeld model. Now today what we will do, the electron will see the ionic core and see how the interaction of that electron with respect to this ionic core. So before going to that, what's our taught is like anisotropic and periodic potential. So normal typical solid, it will be anisotropic, like it looks like isotropic because of its polycrystallinity. So there are three kind of classification you can see here. First one is single crystal. So here in case of single crystals, like atoms will be arranged very ordered. Okay. Another one is polycrystalline with larger crystals. So here it will be like there will be several sections will be there which atoms are arranged in a particular manner. So but each section domains will be different. But in case of polycrystalline material, what will happen, that like arrangement of atom which will be very in the very small area, then like the partition will be very high and it will be very small. So that is polycrystallinity. Okay. So inside this polycrystalline, so what will happen here, the atoms will be arranged. So that arrangement to the another domain, it will be different. So which is the another one will be different from other two. So in single crystal, what will happen, that atoms will be arranged, so highly directional dependence and no cleavage of this atomic plane. So but in case of single crystal, what will happen, like this I told, it is very directional dependent. So in that situation, when the free electrons will have, when if the free electron is which is present in this single crystal, if we measure any quantities like resistance, resistivity, all those things also will be directional dependent. So this, like for particular, if from here to in this direction the value will be different, from here to here the value will be different, because it is anisotropic and as well as the highly directional dependent. So this difference in the properties with respect to the direction, which we can call it as anisotropic nature. Now if we see polycrystalline with large crystalline material, we can see some anisotropy, but the degree of that anisotropy will be comparatively less compared to the single crystals. So here also now let us consider in this case, in this particular direction it is R1 and here R2, then the difference delta R will be comparatively less compared to the single crystal. But in case of polycrystalline, it will be isotropic because it is not depending on the direction. So here what will happen, the properties which in corresponding to particular orientation will we have to take as averaged. Okay. So when we discuss the free electron model, there were no anisotropy. So because there we have discussed the conductivity, that is Ne square tau by m. Here there is no directional term. So which is discussed, whatever we discussed with free electron theory, this is for the isotropic system. Now we have to see how electrons will see when we see this anisotropic nature, how the interaction will be. So for that, first consider single electron and see how the ionic course interaction will be. Then we will go to the multiple electron case. Okay. So here this center that we can consider as the ionic core. So like if electron is very far away, like minus infinity plus infinity we are considering, and this axis will be potential. So electron will be negative and ionic core will be positive charge, so there will be attractive force on between them, right? And it will be Coulombic interaction. So the potential value will be minus 1 by 4 pi epsilon 0 E by R, because E electron will be negative charge and will be positive charge. So if you see from this formula, what will happen if the electron which is far from the ionic core, like here, what will happen, the value will be sent towards to 0. So this, but still it is negative value, so it will be like when electron moving towards the ionic core, what will happen, that will be R value will reduce and come near to 0, like ionic core distance when reduce, it will go to the larger value but still negative one, so it will come as like this. Okay, so when the distance decrease, the potential will also get the decrease. Similarly in the other side also, so it looks like identical. So this in the case of the single electron. Look into this case of a single ionic core, but in the case of solids, what it will be periodic arrangement of ionic cores, so that many electrons will be there. Now let us take 3 ionic core examples here. So if you see the first ionic core, the potential will be like this. Okay, the second case, what will happen, the potential will be like here. Okay, so the green color line which is marked here. So when we look at the overall solid, what will happen, when the electron which ended towards the ionic core, it will go to the potential value of the first one, then towards the next one. So you can see this red color. Then potential will increase from one ionic core to the next one, like in middle distance between these two. Then you see the next one, then it will decrease again. Similarly, it will increase and decrease here. Okay, so this nature will continue. So finally, what we will get. So here this red color line, which is the normal potential character of this electron when it see the ionic core. Okay. So we'll do take an approximation for the 1D crystalline solid, and what will happen. So here this dotted line which contains ionic cores. Okay, here 1, 2, 3, 4. So when we consider the free electrons, it doesn't see the solid, so it will be out of solid. That will be considered free electron. The potential will be 0. So as soon as we the electron consider the ionic core, like it ended to the solid, what will happen normally? So there will be little drop in potential to the negative direction, like it will be drop. So here we can get the atomic well. So this potential which is produced by the atomic well, it will like a bound electron then here. So we can get a square well potential in this case. So what is the common normal nature here? Outer the potential it will be 0, but inside the solid, like it will be negative value. So this valence electron nothing but which is donated by the each ionic core, right? So those electrons which will free to move to the entire lattice from here to here. So here we can see the electron which is loosely bounded to the nucleus, so that will be like bounded electron in this square well, so they cannot move out of this well. Okay. So now you know about the work function, the minimum energy required to get out this electron from the potential well, and this distance we can one have x and another one we can take it as a. So we can the de Broglie format is P is equal to h by lambda, so that we can just rearrange it like h by 2 pi into 2 pi by lambda. So this we can call it as h cross by k, h cross into k. So p will be this first equation, where h cross will be h by 2 pi and k will be 2 pi by lambda. Okay. Now momentum will be what? mv, so velocity, and the energy will be half mv square. So substitute those m multiply with numerator and denominator, will get p square by 2m. So p we can substitute, so energy will be h cross square k square divided by 2m. Okay. So here what we have to find is what will be the allowed values of lambda for each solid, and why the energy spectrum is discrete. So these two and similarly how this energy, the relation between energy and lambda, or the relation between the energy and the wave vector. So that if we get to know about these details, we'll get the idea about how the electron will interact in a solid, or which will be nothing but matter. So here if you see, before going to this electron nature in the crystal, first we will see how a string which is attached to a like bounded to one end, like another one will be free to the free end, one will be the bounded one to the wall. So consider if one end is open, then for particular this kind of system, all wavelength will become possible, because the smaller one or the bigger one, whatever the wavelength we are giving, all this wavelength will be supported. But if you see wall to wall connection between the string, then it won't be like satisfy all the wavelength, like it will be restricted ones. We are giving the constraints to the system. So here E square is equal to h cross square k square by 2m. So here if you substitute the value, then h cross square by 2m into 2 pi by lambda square. So here we can, the values of lambda, we can take anything, so it will be continuous vector. But if you see in this case, second case, like here, first one, the red color one, with half lambda, like lambda by 2 value, like from at distance a, it will be like this one, lambda by 2, lambda 3 lambda by 2. So this will be the values only, particular values only which is available. So here, like if a string lambda 2 ends, what will happen? It will be confined and like quantization value will come. So how the wavelength will happen? So x equal to 0 and x equal to a, the displacement, how it will be, that will be 0. Okay. So the corresponding to a value, like it will be 3 lambda by 2, 4 lambda by 2, etc. n lambda by 2. So the allowed modes for particular a value, that will be n lambda by 2. So we can write the energy then here, substitute h cross square k square by 2m. So that will be like h cross square n square pi square by 2m a square. So discrete energy value will be there. So here you can see this is a realistic picture of this ionic core. It will be like this ionic cores and how the electron will interact with it. Okay, so it's like it's a function of position in the solid. So reasonable approximation which we can see here, this one. So recognizing this idea, confined to the electron, like confined will be two kind of nearly free electron, that confinement scale of them, and another one is the bound electron state, that confinement at the scale of the angstrom. Okay. So if analogy with the to the waves on the strings, so if no restriction will be therefore when the lambda, if it will be like, or if one end is clamped, but if the two ends are clamped, then it will be like there will be restriction, so we will get the quantized value. Now this confinement leads to the quantization. How it will be, like we can see that. So we found the energy value, that will be h cross square pi square n square by 2 ma square. Now we know the Schrodinger waves equation, that will be minus h cross square by m by 2m d square psi of x divided by dx square plus v of x psi of x is equal to d psi of x. So here this will be potential energy, this will be what will be kinetic energy bar, and E will be the total energy. Now this we consider in the truly free electron case, that will be potential will be 0. So then the equation will, the potential part will be 0. Then Schrodinger equation become like d square psi of x d by dx square plus 2m e by h cross square psi of x equal to 0. Okay. So then we have to find the solution of this. So here you will get minus of k square into a cos kx plus b sin kx. So this is nothing but your original wave function. So it will be like minus k square psi of x. So then from there k square value we know that like 2me by h cross square, or otherwise easy h cross square k square by me. So k will be plus or minus root 2me by h cross square. Then so this will be like d square psi by dx square is equal to a of minus k cos kx plus b of k times minus k sin kx. Then we will get the value like minus k square psi of x that we are seeing here. Okay. So here what you will get, all the value of energy will be allowed, so it will be like a parabolic curve. So this will be the Schrodinger equation and value for the truly free electrons. Now we will go to the another one, electron trapped in a potential. So in this case what we have found, that electron will only trapped in between 0 to a distance, then remaining outside the potential well, the psi of x will be 0, the inside will have a value. So then Schrodinger equation will be inside the well, like v of x equal to 0, we can write it as here, then we will get d square psi of x by dx square plus 2m by h close square psi of x equal to 0. From there we can assume the value psi of x equals kx plus b sin kx. Now boundary condition need to apply, psi of 0 will be 0, psi of a will be 0. So this we have to apply these two boundary condition and solve this equation. Then we will get the value of k is equal to n pi. So k is equal to n pi by a. So it will be like function like this. Okay, so then energy we can write it as h cross square by square n square divided by 2m square. So here the energy will be condensed with the n value. So then the potential will be like this. So bound electron confined with an A, that will be k is equal to n pi by a. So nearly if electron will be with respect to L, then we can write as k n pi by L. Okay, so that's the value like we can see here. So if we see electron which is bound within the L, so that is which is related to the volume of the material. Then the dispersion relation will be E versus K curve will be like the gap between these two will be like 10 to the minus 11 value. That very small, so we will feel it as a continuous one, but actually which will be the discrete values. Okay. So now we will go to the problem session. First just go through whatever we had discussed now, then we will start the problem solving session. go to the problem solving session. So here first question dash shows the perfect atomic orientation and different properties in different directions. So the options are like single crystal, polycrystals having few large crystals, polycrystal having smaller crystal, and polycrystal having smaller size crystal with random orientation. So here you have to see the point like perfect atomic orientation and the difference properties of different one will be like answer will be single crystal. Now see the next question. Polycrystals with much smaller size and randomly oriented crystals have dash properties, while graphene material shows which properties. So here what is the much smaller size and randomly oriented? So it will be anisotropic character. And graphene material will be what? It will be anisotropic. Like was our already taught about the graphene as anisotropic nature, so that will be the answer. So now third one. The potentiality of the photon approaching towards ionic cores will be what? And at the infinity becomes. So here it will be how it will be look like. Is equal 4 pi epsilon naught by r, right? So it is approaching towards ionic core. For example, if it is ionic core, so when it goes towards the ionic core, it is decreasing, right? See here, in a meter long solid, nearly free electrons are dash and bound to electrons. So free electrons are here. What will be the answer? Like the options are free to run across the solid and confined to the ionic core, confined the few angstroms and free to move within 1 meter distance, confined to the ionic core, free to run across the solid, free to move within 1 meter and confined few angstroms. So which one will be the answer? Free to run across the solid and confined to the core, right? So here what will be the answer? Nearly free electrons and bound electrons and the large confinement range. So this will be the answer. Okay, this will be the answer. Okay, and now next one, see the table below shown the condition as a result due to the any result due to the condition. Based on this we have to choose okay, so here truly free electron, then what will happen? A and C will be true and B will be false. Right. If truly free electron, no restriction of lambda to like be if continuous spectrum. Electron condension matter, any discrete set of lambda can be. That's wrong. Now if you see the Schrodinger equation, minus h goes equal to 2 and d square psi of x by dx square plus b of x psi of x is equal to e psi of x is the sum of what? It will be the kinetic energy and as well as the potential energy of the system. Now if you see this one, third question, ionic core is in a solid was ignored in which model? Doo's model and as well as the Doo's-Sommerfeld model. Now see, when electron passes from one end to another end of a solid, it feels the difference environment because of the ionic cores. Like all of these, right? Ionic cores begin for free electron, nearly free electron and bound electron. If you see this one, nearly free electron, like we have to identify the following points, like which one is A point, B, C, D, E. So first one will be what? This marking, this y-axis will be potential energy. So then from here this option will be the correct potential energy, and second one, this situation will be nearly free electron, and C will be this Fermi energy level, and D will be the difference, right? So it will be like the work function, the minimum energy which is needed, and A will be the E will be the axis will be lattice position, so it will be E versus K curve. Okay, and then here we can see the bound electron positions. Now see here these questions. A potential in a material will be his representation of a potential energy experienced by an electron under the influence of ionic core. Nothing but that it can be d by specific location in its atomic dimension in some location, and as well as the difference of a free electron and the nearly free electron. So all of the above, which all are the correct answer here. Now see, the value of our function of a material is what? It will be the positive value, or function of a material that will be positive value. Now Schrodinger equation can be represented by the kinetic energy and the wave equation, which consists of the kinetic energy and the potential energy terms. And we have discussed now the graphene displays anisotropic nature because of what? Its crystal structure, nothing but. And when and only one end of the string is tied, the waves of any wavelength can move on it. But when both ends are strings are tied, then wave has some restriction imposed on its wavelength. Does it hold true for a particle example of violin string of length around 20 to 30 meter? So what will be the answer? Yes, right. If it is tied in both sides, then the answer will be yes. The reason will be what? Because of strings are tied on the both end. Now here we will discuss some problems which are related to the week 6 class. So here the question is, system contain energy E1, E2, E3 etc. in having the state 2, 7, 9 up to 14 and particle 1, 5, 3 etc. 5 respectively in it. So how many different ways can be arranged the empty state along in the energy level E3 while this is in microstate case? Here we have to discuss the arrangement of state, and that we have already discussed in the last class. You will get the answer. 720 will be the value of it. So here I am marking the answers. You can cross check it later how it is coming. Okay, so now see the most probable arrangement is what? Significantly larger than sum of all the old terms. Now see here you have to match the following. So T is equal to absolute zero temperature, T greater than the absolute temperature. What are the probability occupancy of the system? Right. So here answer will be this one, like E will be 3 for absolute zero temperature, F of E will be 0 when E greater than EF. Then B will be fourth one, like F of E is equal to half when E is equal to EF. Just go through the questions what we have discussed. remaining. We will meet in the next class.